Hello and welcome to the third and final video on the graphical solution of linear programs. I'm Dr. Scott Stevens, and this part is kind of a wrap-up of some extra things that we really need to talk about, possibilities for linear programs, and tricks that can make this work a little easier. So, a quick reminder of what we've been doing. We had this problem about making and selling fireplaces and putting some salespeople in the field to increase our sales if we wanted to. Our goal was to maximize profit, and we had four constraints that we had to satisfy. We couldn't spend more money than we had. We couldn't sell more units than there was demand for. We had to make at least 60 fireplaces to satisfy a previous contract, and we couldn't make more fireplaces than our factory could handle. We approached this with a graphical approach of drawing a picture. The straight lines with their numbered are identified as the constraints. The blue region is the feasible region, which corresponds to all possible combinations of F and S. That is, values for fireplaces and for salespeople that don't violate any of the constraints. Our goal then was to find the best solution among those points. Part 1 of this series was finding out how to find the blue region. Part 2 was, given the blue region, how to find out where to put the star. This is Part 3. About some other things that can go on. We notice that the optimal solution here, which we found by solving the equations for line 1 and line 2 simultaneously, gave us an answer of 172 fireplaces and 13 salespeople, making a profit of $102,900 a week. Not too shabby. When you work out the numbers to make sure that all the constraints really are satisfied, here's how they come out. I've stuck in F equals 172 and S equals 13 in the program I just showed you. On the budget constraint, you see we make it, but with none to spare. We use all $125,000. On the demand constraint, we make it, but with none to spare. The original demand was 120. Our 13 salespeople increased that to 172, and we made 172 fireplaces, completely satisfying demand. The other two constraints are also satisfied, but they're satisfied with some to spare. This idea of being satisfied with none to spare or some to spare is an important one, and it's what I want to talk to you about. We actually could have figured out that we used all of our money and that we met all of our demand exactly without doing any calculations at all. Because the point that we're looking at, the star, the optimal point, is on constraint line 1 and on constraint line 2. Remember that we drew these lines by setting the two sides of the constraint equal to each other. So when you're on a constraint line, you are satisfying that constraint but with none to spare. You have none left over at all. The leftovers are called the slack. So I'm saying that constraint 1, where we used all available money, has $0 slack, and constraint 2, where we couldn't exceed demand, also has 0 slack. A constraint that has 0 slack is called binding. So those two are binding constraints. And frankly, the optimal solution is determined by the binding constraints. If you imagine that I took constraint 3 and wiggled it around a bit, or changed its slope a little bit, or even moved it entirely, I hope that you see that it wouldn't change where the optimal point is. That's true for constraint 4 as well. But wiggle or move constraint 1 or constraint 2 a bit, and that star is going to jiggle around too. So it's the binding constraints that a manager really wants to pay attention to. The non-binding ones are of less importance because they don't directly determine the optimal point. So constraint 3 and constraint 4 are both non-binding. They don't pass through the optimal point. The non-negativity constraints are also non-binding, the ones that force us into the first quadrant. But if you look at constraint 4, it's even more than non-binding, it seems, in that it seems completely out of the problem. Constraint 3 at least forms a side of the feasible region. Constraint 4 didn't even do that. If you took constraint 4 entirely out of the program, the feasible region, what's possible, would remain entirely unchanged. That makes constraint 4 a redundant constraint. A redundant constraint is a constraint that its removal would not change the feasible region. It doesn't even change what's possible, let alone what's best. Redundant constraints can be safely ignored because if you satisfy all of the other constraints in the problem, it is impossible to violate a redundant constraint. In this problem, if you satisfy constraints 1 and 2, there is no possible way that you can violate constraint 4. So, if you're trying to figure out what constraints to focus on, maybe you can make them a little easier to satisfy, for example, it's the binding ones that you care about. Changing the binding constraint may, and probably will, change the quality of your optimal solution. If you change a non-binding, non-redundant constraint, you will change the feasible region, but you won't change your optimal solution. A redundant constraint is even more irrelevant. A redundant constraint can be ignored entirely and removed from the program without affecting the optimal solution or the feasible region. You can tell a constraint's redundant because it doesn't form one of the walls of the feasible region. If you imagine the feasible region as being a swimming pool full of water, removing a redundant constraint will not make any water leak out. Removing a non-redundant constraint will. Okay, that basically handles the terminology. But I want to show you what can happen when you solve a linear program, because what we had happen in our example is the most common, but by no means the only possibility when you get the solution to a linear program. What we had, as you can see on the right-hand side, was that we found an optimal solution. It was the only optimal solution because it's the only point which is both on the optimal OFL and also inside the feasible region. The only way that you can make the most money in this problem, the biggest possible profit, is to make 172 fireplaces and to hire 13 salespeople. But there are other possibilities. One other possibility is that the feasible region doesn't exist at all. Here I've made a little change in my program. Constraint 4 used to have its arrow pointing to the left. I've just changed it so the arrow points to the right. That is, constraint 4 now says you have to make at least 240 fireplaces. Well, it turns out that's impossible to do. I can't meet my budget limitations and my demand limitations and also make 240 or more fireplaces. There is no feasible region for this problem, which means not only doesn't it have a best answer, it doesn't have any answers. A program like this is called infeasible. And the only way you can get an answer to it is by making one of the constraints easier to satisfy or removing it entirely. Another possibility is basically more than one optimal solution. This happens in a very specialized situation where the original OFL, when it passes out of the feasible region, does not leave by way of a single point, but instead leaves by way of an entire line segment. Here you can see if the original OFL is moved down and to the right according to its arrow, the last thing it will touch in the feasible region is all of the points marked in red, and in fact all of the points between them as well. Any one of those points is an optimal solution. So that would happen in this problem if the fireplaces if the profit were $625. It would tilt it just enough to make this happen. If the line's a little bit more tilted or a little less tilted, this problem would have a unique optimal solution. The last possibility is that the program is unbounded, and this is the one that you have to be a little careful with. An unbounded program is really the opposite of an infeasible program. In an infeasible program, there isn't any best solution because there aren't any answers at all to the problem that are possible. In an unbounded program, in some senses, there's too many solutions. No matter what answer you find, you can always find one that's better. Here's an example of what the feasible region might look like in a potentially unbounded program. I've just reversed the arrow on constraint line 1 to basically say you have to spend at least $125,000 in our fireplace problem. Now the feasible region goes on forever, as you can see it scrambling up to the top of the screen. That means the feasible region itself is unbounded. And it's true that any program which is unbounded will have to have an unbounded feasible region. But gang, that isn't enough. An unbounded feasible region does not guarantee an unbounded program. Let's see why not. It depends on the direction of the OFL. I've shown you the optimal OFL for this problem. Its arrow is pointing down and to the right, so the line that I'm looking for is as far down in that direction as you can get. And in fact, the line that I've drawn is such a line. The feasible region goes on forever, but I have no interest in going on in that direction. This is an unbounded feasible region, but a bounded program. But now, reverse the direction of the arrow on the OFL. Suppose it were running that way instead. If it were, our goal now would be to move the line as far as possible in that direction so that any further movement would make it leave the feasible region. But remember, that feasible region goes on forever up there, and so does that OFL. So no matter how far you move this line in the direction of the arrow, it's always going to cross the blue area. That means no matter how far you move it, it's still feasible. That means the objective function, the profit, can get infinitely big and still be possible. So this has no best answer because no matter what answer you find, there's a better one available as well. That makes it an unbounded program. That last example was in some ways kind of silly, since its objective with the arrow pointing upward was to minimize your profit. Here's one that might make a little more sense, and a simple example of an unbounded program. I'm going to maximize x subject to the requirement that x has to be at least 5, and that's the only requirement. Well, the feasible region allows all x's that are bigger than or equal to 5. And as x gets bigger and bigger and bigger, my objective gets better and better and better. If you say, how about x equals a billion, I'd say, how about x equals a trillion? My answer is better. If you say, how about x equals a gazillion, which doesn't exist, I'd say, how about a gazillion and one, which is still bigger. No matter what value you pick for x, I can always pick a bigger one that will give me a better answer. That's what makes it unbounded. If this were a minimized program, it has a perfectly good answer. The feasible region goes on forever. All the numbers bigger than x are still okay. But x equals 5 is as small as you can possibly get it. In real life, unbounded programs hardly ever happen. Well, they never happen, because something is going to stop you from doing something forever. I don't know what it is, but it can't go up to infinity, so you're leaving some constraint out. But infeasible programs certainly can happen. You've got constraints that are too picky, that are too demanding, and they can't all be satisfied at once. Either some constraints have to be removed, or they have to be eased, or else you're wasting your time. Alternative optima can be nice. If you've got more than one answer which gives you the best answer to your problem, then you've got more than one way to approach the situation. There may be some other factors that are worth considering that you can now consider because they won't cost you anything. And a unique optimum with only one optimal answer is certainly the most common thing to happen. Now a couple of other things that we should talk about, and then we'll wrap this thing up. Sometimes the program will include an equality constraint itself. It won't have less than or equal to or greater than or equal to. In this case, you're going to draw the line that corresponds to that constraint, but it won't have a good arrow. Okay? You'll have to be on the line. So if our first constraint had been an equality, the feasible region would be just that red line, because you have to be on line 1 in order to be feasible. Here's something else that can happen. A line that goes through the origin. The intercept approach is going to fail because you'll find the x-intercept and the y-intercept both to be 0. You can recognize these equations because when you look at them, they don't have a constant term. For example, my example of 4x equals 6y doesn't have 4x plus 6y plus 10, or 4x equals 6y minus 2. The constant term is 0. When you've got that, you do not want to draw a 45-degree line. You want to figure out another point on that line. Here, I picked the value x equals 12. I could pick anything, and plug that into the equation to see what y happened to be. In this particular equation, when x is 12, y has to be 8. So the line goes through 0, 0, as we knew, but it also goes through 12, 8. If we have to find the good side for such a line, we can't use 0, 0, and I hope you know why. The line goes through 0, 0. Okay, a couple of other things. If you take a look at a constraint and you change the numbers in it, you're going to affect it in a very specific way. Take a linear expression and change the constant term, and you'll get what happens at the bottom picture, where the red arrow shows. Changing the constant term will leave the slope of the line at the same, but it will change its y-intercept. You'll be moving parallel to the original line. On the other hand, if you change either coefficient in the original expression, ax plus by, either number in front of a, either the a or the b, you're going to have an effect like you see in the upper picture. That is, an intercept will stay the same, but the slope will change. So if you're going to be changing one of the coefficients, you're going to be changing the slope. But if you change only the constant term, you'll be leaving that slope constant. And these will be important ideas when we get to Chapter 5. Finally, a little trick to help you with the OFL. We already know that we can use a test point there, but this is a way that you might find nice and fast. In order to use it, you have to memorize these two pictures, the max picture with 4 arrows pointing out, and the min picture with 4 arrows pointing in. I think the easy way to remember this is min points in. So, we look at our program, and then we'll look at the objective function and the coefficients that appear in it. For example, here was our objective problem for the function for this current max problem. I want to look at the coefficients, the numbers in front of my variables, f and s. And I only care about their sign. Are they positive or negative? Here, it's a max problem, so I'm using the picture on the left. The f coefficient is a positive number, positive 1,000, so I'm going to circle the positive f-axis. The s coefficient is negative, it's negative 2,500, so I'm going to circle the negative s-axis. Now those two little ovals that I drew isolate one arrow from the other three. In this case, it's the one pointing down and to the right. So that is the direction that my OFL should move, down and to the right. This trick works with every problem. You'll use the min picture for a min problem, the max picture for a max problem, and you'll label the two axes the same way they're labeled in your graph. That makes life pretty easy. Finally, you might not care, but I've only been doing this stuff with two variables and said you could do it with more, but it's hard. If you had 3 variables, the feasible region would look something like the green crystal that you see on the right-hand side of this page. The blue plane would be your objective function line. It would now be an objective function plane, and we continue moving it, flooding that crystal until, for a max, the last point would be submerged, or, for a min, we lowered the water until the last point came out of the water. Mathematically, the results are exactly the same, but in terms of drawing, it's a bit of a challenge. That's it. We're done Chapter 3.